So we're told we want to find the power extracted by the turbine in the system shown below. Pipe entrance is sharp edged, so that just means right here. This is a sharp corner. And the volumetric flow rate is given. Density of water and the kinematic viscosity of water is given as well. So we want to determine the power extracted from this turbine. So what do you think the first thing is that we want to do? So what tools are we going to use to analyze the problem?
On the right, extended Bernoulli equation.
The extended Bernoulli equation. Pretty much all of these pipe flows comes down to the extended Bernoulli equation. So we'll write the extended Bernoulli equation. And you'll have done enough of these, you'll memorize the equation. It just looks like Bernoulli's equation. I like to take a shortcut and write it like that. The dot, dot, dot here just refers to, it's the same thing as this. I just am lazy and I don't want to write it all a second time. So in that extended Bernoulli equation, we need to go from some point 1 to some point 2, right? Some inlet to some outlet. So now, what should we use as our inlet? What should we use as our outlet? Yes?
Inlet, maybe the free surface.
Free surface is the inlet, okay. What about the outlet?
I would start with maybe the exit of the pipe.
Yeah, those are excellent points. So there's some streamline that goes that way. For the choice of points, there's some guidance I can give you. Number one is you generally want to choose points where you have a lot of information, just like with Bernoulli's equation. So on that free surface, we know the elevation, we know the velocity, we know the pressure. Similarly, here at the exit, we know the velocity there because we know the flow rate and we know the pipe diameter. We can get the velocity. What's the pressure there at the exit? Atmospheric, because it's a free jet. It's just going into the atmosphere. And we also know the elevation relative to the point 1. So we have a lot of information there. So choose your points where you have lots of information. Then the other piece of guidance is you want to choose points such that you capture the information you're interested in. So in this one, we're interested in getting the power extracted by the turbine. So I want my streamline to pass through the turbine. So where is the turbine power going to show up in my extended Bernoulli equation? Yeah, it's going to be the shaft head term. The HL12 and the HS12 just means what are the total losses between points 1 and 2? What's the total shaft head between points 1 and 2? So the power is going to show up in this HS term. So the next step that we take is, well, what do we do next? Let me ask you. Yeah.
Just write down what you have.
Yeah, so let's just, we have this equation. Let's write down everything we know. So I just already said that the pressure at 2 and the pressure at 1 were both atmospheric. The velocity at 1 is about equal to 0. It's very small. It's not exactly 0, but it's super small. Velocity at 2. How do I find the velocity at 2? The average speed or average velocity at 2. How would I do that? I actually told you what to do just moments ago. Think about what's given and how you would use that information to find the velocity. Yeah, the volumetric flow rate. So how do you go from volumetric flow rate to velocity, average velocity?
Divide by the area.
Yep.
Divide the volumetric flow rate by the area.
Exactly. So we'll say the volumetric flow rate is Q. We'll divide by the pipe area. I'll just call it A. So just so you have it, and I'll just write down the number here. So that we're given that the volumetric flow rate is 0.004 cubic meters per second. And then the area, it's a circular pipe. Pi over 4 times the diameter, 0.05 meters squared. So you can find that, and I worked that number out. It comes out to be 2.04 meters per second. Unfortunately, with with a lot of these pipe flow problems, there are lots of numbers floating around. You just can't get away from it. I highly recommend that you put your units along with your numbers. Just do it, because otherwise it's very common to see people make units mistakes. They know the final answer should be in terms of watts. So they'll put all the numbers, no units, and then at the end get a number and just slap watts on it. But it's very easy to make mistakes where, is it kilowatts? Is it milliwatts? You know, like you might be off by a factor of 1,000. You know, it's easy to make those mistakes. So put your unit, especially for homework, you've got plenty of time, put your units on there and just make sure they all make sense. Okay. All right, so how about, let's do Z1 minus Z2. What do we do for that?
Given us 40 meters.
Yeah, it's just from the picture you can see it's 40 meters. And it's just this Z1 minus Z2. You can see the distance is 40 meters. Okay, one other thing that I guess I didn't put is I didn't talk about this alpha. So we don't care about alpha 1 because V1 is 0, but alpha 2 we need. What do we call that alpha again? It's you got part of the words right. It's the kinetic energy correction factor. So what is that value going to be? That's right, it depends. What does it depend on? Laminar or turbulent. Well, how do I figure out whether it's laminar or turbulent? Calculate the Reynolds number. So let's just do that down here. So the Reynolds number is going to be the velocity at 2. So we're calculating the Reynolds number where we're interested in finding the kinetic energy correction factor. So it's going to be V2 times what? What do I put? What's my length scale? Diameter, yep. So diameter, so the same diameter through the whole pipe divided by the kinematic viscosity. So the V2 is 2.04 meters per second. The diameter was 5 centimeters. Kinematic viscosity is given in the problem statement. I won't write those down just for the sake of time, but the Reynolds number, what does the Reynolds number come out to be? It comes out to be 101,500. So what does that mean now?
Turbulent.
Turbulent. Like, what's the dividing line between laminar and turbulent pipe flows? 2,300. Right. So this is greater than 2,300, which means that it's turbulent. So what does that mean about my alpha? It's about equal to 1. Okay. All right, so far so good. So now we need to move on to the HL and HS term. Let me start with the HS term. That's the shaft head term. Ultimately, I've said before that term contains the turbine power, but how's that related to power? That's a shaft head term. What are the units for HS? Length. That's right. It's a head term. So how do I relate that to power?
Power over the mass flow rate.
Yes, you're missing one little bit. So the power, I'll just write it as W dot, divided by the mass flow rate, and there's one more term there.
Oh, gravity.
Times gravity, gravitational acceleration. That's it, yep. So that's how you relate the power in the shaft head term. It's W dot over M dot times G. Okay, so this is the term we're going to ultimately solve for. Yes?
Is the alpha that we found the same for both 1 and 2?
Actually, the alpha for point 1 would actually be, it's just not defined because it's point 1 has 0 velocity. So 0 times anything, it doesn't even matter. But if you did want to calculate it, it would definitely be laminar because the velocity is not 0, but it's super close to 0. So that would make the Reynolds numbers really small. So it would effectively be laminar. Yeah. How do I find the mass flow rate?
But volumetric flow rate times density.
Close.
Multiply.
Multiply. Yep. Density times the volumetric flow rate. And if you put your units down, you'd catch it. catch the, its density times the volumetric flow rate. I don't think I wrote that number down. But anyway, that's how you would find it. Okay, so that takes care of the shaft head term. Let's say that the turbine wasn't in there. Let's say I was analyzing this problem and we didn't have a turbine. What would be different for that HS term? So there was just nothing. The turbine was gone.
Zero.
It'd be zero. There's no shaft head term. Right? So it's only there if you have some sort of rotating machinery, some sort of fluid machinery that either adds energy into the flow or takes energy out. The turbine will take energy out. We should, since I said it was a turbine, we would expect the W dot to be negative in the end when we solve for it, because that means it's pulling energy out of the flow. Okay, now the last term is the, what do we call that one? HL?
Head loss.
It's the head loss. It's where all those viscous losses are. So that's equal to, I'll just write it this way. This is the loss coefficient, K. I'll put a sub I there. Talk about that in a moment. But it's going to be all of our various places where we have losses. So that's why I have a summation. That's a summation, it's just small. K sub I, that's the loss coefficient for some particular loss. There'll be several of them. And then the V bar squared over 2G, and there's a subscript I in that. That's the velocity head where that loss occurs. Okay? So just make a particular note, write this down, that this V sub I, this is the velocity where the loss is occurring. Because you may have pipes with different diameters and the velocities are different. You want to be using the correct velocity. It's the velocity where the loss is occurring. So let's take a look here and see what kind of losses we would have. So what do we broadly lump the losses into, like two categories? Major and minor. So let's start with the major loss. So how do I find, okay, so let me write, let's figure out what the major loss is here. How would I find that? Do you know how to find a major loss coefficient, the K for the major loss? That's you're thinking of minor losses, but for a major loss?
Coefficient times the length over diameter.
Exactly. So I'll just write it as K major. But that's equal to, the major loss is the friction factor times the length over diameter of the pipe. So it's the friction factor for the pipe times the length over the diameter. So what would be the length that I use?
125.
125. Let's give it up there that the length of the cast iron pipe is 125 meters. And then the diameter we already know is 0.05 meters. It's 5 centimeters. We'll come back to the friction factor in a moment. Actually, you know what? Let's do the friction factor now instead. So how do I find the friction factor? Is it 64 over the Reynolds number? Do you remember that from your reading? What is that? What is 64 over the Reynolds number?
That's for laminar flow.
That's a friction factor for a laminar flow. But we know this one's turbulent. So then how do we find the friction factor for this turbulent flow?
Moody plot.
We could use the Moody plot. That's exactly it. So if we use the Moody plot, what does the friction factor generally depend on? Like just in general, the friction factor is a function of what quantities? What are the axes on your Moody plot?
The Reynolds number and the relative roughness.
Exactly. Reynolds number and relative roughness. We have a Reynolds number, but now we need to find the relative roughness. Okay. So the Reynolds number is 101,500. Well, actually, before we do the relative roughness, let me just go back to let me pull up the Moody plot. So here's our Moody plot, 101,000. So here's 100,000 right there. Right? So, we're pretty close to it. So let me do my best to draw a straight line straight upward. Okay, so it's about 101,000, right about there. And so now we need to find the relative roughness. So how would I find the relative roughness? We're told that it's cast iron pipe, so what do I do with that information?
That's how it's calculated.
Yeah, so we can, let me go to a different plot. So if you go to your formula sheet, for example, you'll see a table in there that says the average roughness for commercial pipes. So we'll go, okay, cast iron. Come over here, 0.26 millimeters is the roughness we'll use. Now, keep in mind that these are all just very approximate values. You know, we're doing calculations by hand here. You know, I'm sure there's a wide range of roughnesses for cast iron, depending on how old it is and stuff like that. I guess here it says, you know, it's new material, but depending on how it's manufactured, you'll get a wide range. So treat these values as being, you know, just ballpark values. They're not the exact value. If you really needed an exact value, you would actually have to go out in the lab and measure the exact value for that pipe. Yeah.
Did you like make that table?
This table came from Frank White's fluid mechanics textbook, I believe.
Okay.
Yeah. So yeah, these tables have been pulled from elsewhere. Okay, so now we know it's 0.26 millimeters. So let's go back to our problem. Oops. So we know the roughness is 0.26 times 10 to the minus 3 meters. We know the diameter is 0.05 meters, so we can calculate the relative roughness. And when you plug those numbers in, what does it come out to be? 0.0052. Okay, so remember that number. So we go back to our Moody plot. 0, 0, 0, oh no, 2 zeros and a 5. 2 zeros and a 5. That puts us 2 zeros, 5. So somewhere right about here. Right? Did I get it in the right spot? So then what I'm going to do is just kind of follow the curve around the best I can. You know, it's somewhere in between those two blue curves, so I'll just follow that until it intersects. Okay? And then when it intersects, what I'm going to do is I'm going to just go straight across and then estimate my friction factor. So like 0.03 something. Does everyone follow that? So when I did it previously, I got 0.032. Yes?
So for the homework, would you be given like kind of like a range of values that are like considered correct because, you know, that's relatively like ballparking right there?
So I've instructed the graders all through the semesters, don't put so much emphasis on the number, put the emphasis on the approach. So yeah, this is all very approximate, so everybody's going to probably get slightly different numbers. It's totally fine. It's going to be within the uncertainty of these measurements, right? So it's the approach we care mostly about. If the TA is taking off points because you have the wrong numbers, like you have to be close, right? Don't put down that the friction factor. Oh, you know, I drew the line here and 0.3. You know, you're off by an order of two orders of magnitude, or 1 order of magnitude. You know, that's going to be wrong. But if you have 0.035 and the TA takes off points, you shouldn't be taking off points for that. It needs to be reasonable. Okay, so now we have our friction factor. And by the way, just make sure you know how to use the Moody plot because it'll be given on a formula sheet, right? And you'll need to use it when you do quizzes and whatnot. But in general, like doing homework, you see these formulas over here? I don't know if I can't flip that easily, but you've got these formulas, the Holland formula, I'm not sure I'm saying it right, and then this Colebrook formula. This is an alternate way to get those friction factors. What those are just curve fits to the Moody plot data. So that's why they look so ugly. You know, they have all these weird exponents and stuff like that. It's because it's just a curve fit to the data, and the people just fiddled with it until it really worked well. The difference between the two is the Holland formula is explicit, meaning you plug in a Reynolds number, and you plug in a relative roughness, and you get the friction factor. The Colebrook formula is implicit. Here's your Reynolds number, here's your relative roughness, but you have friction factor there and there. It's on both sides of the equation. You can't get the friction factor just to one side. And so the Colebrook formula is more accurate. It's a better estimate of the friction factor, but it takes more effort to calculate. So to solve for that implicit equation, you have to do like a Newton-Raphson method or a bracketing method or some numerical method to get in there. So the general approach is you make your first guess using the Holland formula, and it'll be pretty darn close. And then within 1 or 2 iterations using the Colebrook formula, you've got the right, the best estimate of the friction factor. So if you look at my updated book style notes, like the big package, I have an example of a Python code that does that kind of calculation. But I encourage you, for homework to do that sort of thing. It just makes your life so much easier. But you do need to know how to use the Moody plot because that's what you're given for the quizzes. With the calculators you're using on the quizzes, you can't do the Colebrook formula. You can do the Holland formula, but you're not going to be iterating on that. It just takes too long. So anyway, I just want to give you some suggestions there. Okay, so now we have the friction factor. Let me just write it down. So this, we said, was 0.032. What velocity should I use? Remember, I have to multiply it by this velocity head term. So what velocity should I use for that major loss?
Because the conservation of mass uses the V out term.
Exactly. So let's call it V2. The velocity here, it's the same velocity through the whole pipe because it's a constant diameter. So I'll just put down V2 here. So here you can see, like, if my pipe was different diameters, I'd have different velocities, so I'd have to use the different velocities here, if I had different diameters. Yes?
Does that assumption ignore the entrance region?
Well, once you hit here, the average velocity is the same all the way through. It has to be. The velocity profile may look a little different, but the average velocity has to be the same. Okay, so now we have our major loss. Now let's talk about the minor losses. So what minor losses do I have in this problem? What mechanisms cause the minor losses in that picture? Yeah.
Entrance at the
Yes.
turbine.
I'm sorry, say that again. Entrance?
Entrance of the, right there.
Yeah, so we have an entrance loss. Exactly. Anything else?
The valve.
We have a valve. This will be a big loss here because valves are usually complicated pathways. The turbine doesn't present a minor head loss because it's any losses it has shows up, it just decreases the power you get out of it. It's kind of like the power you get out is the ideal power minus whatever losses you have. So it's all those losses associated with the turbine have already been lumped into that quantity. What about an exit loss? There is none because we're not going into some other big tank. It's just coming straight out. It's just discharging into the atmosphere. So in the end, we have K entrance. I'll come back to the velocity head term in a moment. And then we also have the K valve. Let's start with the valve. What velocity should I use for the valve loss? Valve's right here. What velocity should I use for that?
V2.
V2, because that's exactly it. That's the velocity kind of leading into that valve. Okay. So we'll do that. What about the entrance? What velocity should I use there?
Still use V2, correct?
Still use V2. Now, let me write that down and then talk about it. So that's still V2. And the reason for that is that's the only well-defined velocity you could possibly use. Right? If you're going to say, let's use the velocity upstream, well, what's that going to be? It depends on how far upstream you go. It's not well-defined. The only well-defined velocity is once you've gone downstream of that entrance, then it's very clearly defined. When they produce these minor loss coefficients, the tables that you use define them will often tell you what the velocity is based on when they created it. If it's not obvious, they'll tell you. So I'll come back to that in just a second. So how am I going to find these minor loss coefficients, these Ks? Tables. Yep, so let's go back to our formula sheet. Well, here we are. So table of minor loss coefficients. And again, just treat these as being ballpark engineering estimates. The details will depend on the exact make and model of your valve, how the entrance was shaped, all that. These are just rough engineering estimates. And this also comes from that Frank White textbook. So we said that we had a sharp-edged entrance coming in. So I look here, entrances, sharp-edged. So I would use 0.5 for that loss coefficient. Okay, entrance is 0.5. Notice that you have a higher loss the less well-rounded the exit is. So if you look here, well-rounded, that loss coefficient is very small, 0.04. Slightly rounded is 0.2. Square-edged or sharp-edged is 0.5. Because remember that what's causing this loss is the fluid not being able to turn the corner and it recirculates. So if it's really well-rounded, the fluid can make that corner without having to recirculate. Do you guys know what a reentrant inlet looks like?
Where the pipe like sticks out into the tank?
Exactly. So it would be like if the pipe looked like this. So here's your free surface and the flow is going this way. It's where the pipe is actually inside the tank. It's stuck inside there. And there, you can imagine that the fluid really has to make like a sharp thing, almost a 180 turn. So you get really large losses in that case, or larger. Okay, and then the valve. I don't remember what kind of valve we had. It was a fully open globe valve. So here's a fully open globe valve. That has a huge minor loss. It just dominates the other loss. So it's equal to 10. Yes?
What does the constant of infinity like really mean? The swing check backwards flow?
Oh, it must mean that that you just can't have any flow. It's like it acts like a diode in electrical. Flow has to be one way. It's like a check valve. Flow is only one way; it can't go the other way. So if it's an infinite loss coefficient, it just means you can't push any fluid through it. The resistance is so large, you just can't push fluid through it. Valves tend to have very large loss coefficients because they're complicated pathways. You can see on the internet, if you look up what valves look like on the inside, you'll see what I'm talking about. Okay, so we're basically out of time, but let me quickly wrap this up. So now we know these quantities. We have everything we need to go into the extended Bernoulli equation. So what we do is we plug everything in and solve for the power. So do you see all the steps? This is the same kind of procedure over and over again. Okay. Any questions about that before you take off? If you want the numerical value, this is coming straight off of my webpage. So you have all the text written out for you. Any questions before you take off?